After completing this competency, the student will be able to combine reactions and reactors as we bring all the preceding material together to arrive at a logical structure for the design of various types of reactors. So we are going to bring all of the previous competencies, the mole balance, the rate of reaction, stoichiometry, tension gathering. By using the chemical reaction algorithms, one should be able to solve reactor engineering problems by reasoning rather than by memorizing numerous equations together with the various restrictions and conditions under which each equation applies, whether there is a change in the total number of mole, etc. This competency focuses attention on reactions that are operated isothermally, that means at temperature constant. So here we are going to have to apply the algorithm, which is a very nice procedure to resolve this type of problems. Module 1. Mole balance in terms of conversion, the design structure for isothermal reactors. We begin by applying our general mole balance equation to a specific reactor to arrive at the design equation for that reactor. If the feed conditions are specified, could be NH0 or FH0, all that is required to evaluate the design equation is the rate of the reaction as a function of conversion at the same conditions as those at which the reactor is to be operated. That means temperature and pressure. So we have been doing that, putting the rate of reaction in terms of conversion, because here we are going to apply all that. If the rate of reaction is not given explicitly as a function of conversion, we must proceed to determine the rate law by either finding it in books or journals or by determining it experimentally in the lab. So we could go to the Journal of Chemical Kinetics to find different examples for rates of reactions. After the rate law has been established, one has only to use stoichiometry together with the condition of the system, could be constant volume, constant temperature, to express concentration as a function of conversion, something that we had been doing in the last competencies. For liquid phase reactions and for gas phase reactions with no pressure drop, that means the pressure is constant, one can determine the rate law in terms of concentration of the reactant species and use stoichiometry to express concentration as a function of conversion. It is now possible to determine either the time if it's a batch reactor or reactor volume if it's a flow reactor necessary to achieve the desired conversion by substituting the relationships linking conversion and rate of reaction into the appropriate design equation and evaluate. So that's what we are going to do here. By example, batch operation. In modeling a batch reactor, we have assumed that there is no inflow or outflow of material and the reactor is well mixed. For most liquid phase reactions, the density change with reaction is usually small and it can be neglected, so the volume is equal to the initial volume. In addition, for gas phase reactions in which the batch reactor volume remains constant, we also have that B equal to B0, the volume is constant. Consequently, for constant volume batch reactors, the mole balance is 1 divided by B times dNA divided by dt is equal to Ra, equation that we have seen in the first competency. We can write this like 1 divided by b, dna divided by dt is 1 divided by b0 because it's constant. dna divided by dt, we put b0 inside the differential, so it's differential of Na divided by B0, which is the concentration. So at the end we have equal dC divided by dt equal to the rate. The change of the concentration with the time is the rate of the reaction. Because concentration is the measured variable for mole liquid phase reaction, the general mole balance equation applied to reactions in which there is no volume change minus dCA divided by dt equal minus RA, the one that we just arrived. This is the form we will use in analyzing reaction rate data because it's how we obtain in the lab. Let's calculate the time necessary to achieve a given conversion X for the reversible second-order reaction A goes to B. The mole balance on a constant volume batch reactor, we have seen that is Na0 times dx divided by dt equal to minus Ra times B0. And the rate law, because they say it's a second order, is going to be minus Ra equal K, the rate constant, times the concentration of A elevated to the second power. And from stoichiometry, we have that for a constant volume batch reactor, we obtain Ca equals Ca0 times 1 minus X. And the mole balance, the rate law, and the stoichiometry all together will come that dx in dt is equal to K Ca0 times 1 minus x to the square. And here is where we have been applying the algorithm, first to go through the mole balance, then to the rate law, then to the stoichiometry, and then combine them all to obtain the equation for the design of the reactor. To evaluate, we can rearrange and integrate dx divided by 1 minus x squared equal to k Ca0 dt. Initially at t time equals 0, then x equals 0. If the reaction is carried out isothermally, k will be constant, so we can integrate this equation and we will come that dt equal 1 divided by k Ca0 dx divided by 1 minus x squared, and the integral of dx divided by 1 minus x squared is 1 minus x to the minus 1, so at the end we will have that t equal to 1 divided by k Ca0 times x divided by 1 minus x. And this is the time, the reaction time needed to achieve a conversion X for a second-order reaction in a batch reactor. The table 4.1 shows the algorithms to find the batch reaction times Tr for both first and second-order reactions carried out at T constant. We can obtain this estimate of time of reaction by considering the first and second order irreversible reaction of the form A goes to B. So here we have. Here in the row, in the first column, we have mole balance, rate law, stoichiometry combined, and then evaluate. So first we have the mole balance, dx divided by dtr equal to minus Ra divided by Na0 times B. That's the mole balance. Then for the first order, we have minus Ra equal to K Ca, and for the second order, we have minus Ra equal to K Ca squared. And for stoichiometry, we have the same, Ca equals to Ca0 times 1 minus x. And then when we combine those all, we will count that dx divided by dtr equal to k times 1 minus x. And when we integrate that, we come to that TR equal 1 divided by K natural log of 1 divided by y minus x. And for second order, dx in the TR is equal to K CH0 times 1 minus x squared, where TR equals x divided by K CH0 1 minus x. So, for first order the reaction time to reach 90% conversion, that means x 0.9, in a constant volume batch reactor is going to be TR equal 1 divided by K, natural log of 1 divided by 1 minus x, so it's going to be 2.3 divided by K. If we put some K like 10 to the minus 4 second to minus 1, we will come that TR is going to be 6.4 hours, and this is the time necessary to achieve 90% conversion in a batch reactor for a irreversible first-order reaction in which the specific reaction rate is 10 to the minus 4 seconds to the minus 1, and that time is 6.4 hours. And for a second-order reaction, the equation for TR is a bit different, and is equal to x divided by K CH0 times 1 minus x. And if we substitute the same values for x equals 0.9, we will come that TR is 9 divided by K CH0. If we assume that K CH0 is 10 to the minus 3, TR is going to be 2.5 hours. So we know that for a second order, the time necessary is 2.5 hours, and for the first order were 6.4 hours.